So what we plan to do for this session is we plan to give a visualization of all the concepts that we learned in the morning. More than, it's better to visualize all these subspaces and all those things in the first place in, say, 2-dimension and 3-dimension, and then probably look at all kind of advanced concepts. Say, as Professor Shekar mentioned at the end of the previous talk by Dr. Ashok, that it's the fundamentals which matter. So if we understand what's happening in 2-dimension and 3-dimension, it's always easy for us to understand what will happen in a higher dimension. So with that as the motive, Sahil and I will start the session. Sahil will be showing a lot of visualizations, and he'll also be giving explanations for that. Wherever it is required, I'll also pitch in and then give my comments. But before we start, we stopped with a question at the end of the previous session. What are orthonormal functions? I hope people are able to figure out what it is. Or should I write that? So let's basically do this. I haven't yet shared the screen, so I'll share the screen in a minute. I'll just share the screen in a minute. So just a minute. So 2 minutes, then we'll start, okay? So I wanted to look at orthonormal functions. Is my screen visible to everybody?
Yes, sir.
Basically, you look at phi I of t and phi j of t dt, you integrate it, say minus infinity to infinity, whatever that limit that is. This is equal to 1, or probably I should, this is equal to 1 if I is equal to j, and 0 if I is not equal to j. So basically, you can equate this to a delta function. So delta of t, that. Okay. So with that understanding, let's go ahead with Sahil's session.
Yeah, thank you for the introduction. I'm Sahil. I will show you a couple of demos relating to matrices and subspaces as well. So let's begin. I hope my screen is visible to all.
Yeah.
Okay, so we can begin. So we'll start off with 2D matrices, since Sir has said that we should build our foundation from the beginning. So I'll show you a demo on 2D matrices.
See, what happens is, like, most of the times when we just try to solve a system of equations Ax equal to B, let's say even in a 2x2 matrix sense, we really worry about only A inverse, and then we worry about the determinant of the matrix and say that, okay, A inverse is nothing but adjoint A by determinant A. And therefore, if you want to solve Ax equal to B, I need to figure out X is equal to A inverse B. But what does it actually geometrically boil down to? If we get that idea, then we will actually be in a position to understand almost all the concepts relating to your vector spaces and stuff. So we are going to look at that now. Okay. So in this example, if you see, Sahil, can you go ahead?
Yeah. So in this demonstration, we can actually see the effect of a matrix on a sheet of graph. So this basically represents a sheet of graph. These lines would basically represent the coordinate axes which are shifted. So a graph is basically, you have a set of basis vectors, in this case 0, 1 and 1, 0. And each of these lines, these purple lines, are shifted versions of the x-axis, which would represent as a scalar multiplication of this basis. And the blue color lines are the graph lines which are caused by the scalar multiplication of 0, 1. And then shifted over across. So that's what a graph sheet is. So we'll start off with this matrix. So I think you can kind of see this matrix, right? This first matrix. So this is 2, 0, 0, 2. So this basically is the identity matrix multiplied by a factor of 2. So this, what you see here, this gray region, is basically the unit square that has been multiplied by this particular matrix.
Multiplied by that scalar 2. So it's a basically it is the scaled version of that unit square. Okay.
Each of the unit square vectors, which is 0, 1, 1, 0, being multiplied by the matrix, and this is the region which is followed by which is basically the transformation of the unit square.
Yeah, sorry, just 1 minute. I'll add one more point to it. Just have the 2002 only. Now, what is the determinant of this matrix? The determinant of matrix is 4. And if you see that 4 is basically the area of the square. The determinant of the matrix is basically, it's a square of side 2. Therefore, the area of the matrix is, the area of the square is 4. And therefore, we see that the determinant of a matrix in 2 cross 2 sense corresponds to area in some way or the other. It is basically, it's not some way or the other, it is indeed the area. We will actually see that
under the
area of the square. It's area
under
of
the unit, under the linear transformation provided by the matrix.
Yeah. So just change the coordinates, Sahil, then we'll see that.
I'll make it a unit, I'll make it a single matrix.
Yeah, you can make it 3. Well, first of all, let us see like what is happening. Just change the number there alone. So if you basically look at this now, this is a matrix of area. The determinant of this matrix is 2, and that corresponds to your length into breadth of this rectangle. So the length of the rectangle is 2, and the breadth of the rectangle is 1. And so you see that the area of the rectangle is basically 2. So we are clearly in a position to understand that the determinant of a matrix is typically equal to the area of the parallelogram enclosed by the 2 columns of a 2 cross 2 matrix. We'll take a random matrix sign.
Okay.
Probably a differentiable, I mean, 2 instead of 2, 1, probably give a, and so that we could see it very clearly. Yeah, you make it 2, 2, or probably even 2, 4, something like that. Just make it. Yeah. Now, is this that's a good question. 5 cross 5, you cannot visualize at all. Beyond 3 cross 3, visualization is very difficult. Okay, because I mean, all of us are used to only 3 dimensions. And suppose somebody puts a 4th dimension, we'll be in for a surprise. We really do not know how it's going to look like. We can only say that, look, if all these things are happening, it is basically for the understanding of our mathematical concept that we go for this visualization age. And you cannot look for visualization beyond 3 dimension, but all that you want to understand for a higher dimension will all be available within 3 dimensions. So you can understand all the concepts as far as, of higher dimensions with 3 dimensions. That's more than sufficient. See, 2-dimension matrices or 2 cross 2 matrices, they have certain issues as far as certain topics are concerned, which means there are certain things which don't happen in a 2 cross 2 matrix, but that is overcome in a 3 cross 3 matrix. It is like saying, look, whenever I was trying to look at what do you call, let's say it's like the insufficiency of your integers, which made people to think in terms of fractional numbers. Basically, from counting numbers, we moved on to measuring numbers and so on. It's the same way. So if there are certain insufficiencies, that happen in 2 dimension, and that will get cleared in 3 dimension. Is that clear? Now, if you look at this matrix, that matrix is basically 2, 0, 2, 2. Now, the area of this matrix is basically still 4, but this area of the matrix is equal to base into height. The height is equal to 2 in this case. You could clearly see that the height is 2, and then the base is 2 units. So the height is basically 2, base is 2, and therefore you get 4 units, and that is again equal to the determinant of the matrix. So ultimately, what we must remember is, if you are given a 2 cross 2 matrix, the determinant of the matrix corresponds to area of a parallelogram. Remember, if the determinant of the matrix is 0, then there is something that happens. Sahil, can you just make this 2, 0, 0, 0 as also 2? Yeah, all the components 2. Yeah. So if you look at this, yeah, go ahead, Sahil. You can explain.
Yeah, so basically what you saw is that the unit square, that is 0, 1, 1, 0, 1, 0, 0, 1, they get transformed to the same vector 2, 2. So that's what you see here. So the entire unit square, which is spanned by 0, 1, 1, 0, gets transformed to the same line. So instead of seeing a square, a gray square, all you see is a line. So this line is basically represents the transformation of the unit square under this particular matrix transformation. But what you find out is that the area is 0. So this implies that the determinant of this particular matrix is 0, and the determinant will be 4 into 0. I mean, you know, the product of the eigenvalues is equal to the determinant, so that is equal to 0. So that's why we see that this entire gray area shrinks to a line.
So basically, the parallelogram degenerates to a line. Is this clear? And you see, when we had two different columns, which were not multiples of each other, we could actually see that there was something else. There were two different directions as such, or two different variables or two different handles that we had. Whereas when the columns are basically multiples of each other, we have lost one information or one direction, and everything is aligned towards one particular direction. In this case, it is aligned in the direction of 1, 1. Is this clear? So the area of the parallelogram in this case is 0. That means the determinant is 0. That means the matrix is not invertible. Is this clear? If the determinant is 0, the matrix is not invertible. And what it geometrically means in case of a 2 cross 2 matrix is that if the determinant is 0, it simply means that the parallelogram has actually degenerated to a line. Is this clear? And the line has only one measurement, and that is the length. If you take a parallelogram, you have two sides or any kind of, let's say a square or a rectangle, you have a length and a breadth kind of, whereas in case of a line, it boils down to only one measurement. And therefore, we say that this parallelogram in this case has become a line. It is degenerated to a line, and therefore the determinant is 0. Is this clear? Now, there is something more interesting in this. When you have, Sahil, can you make one of those elements to be not 2? Yeah. So now again you see that it has become a parallelogram. The moment I change one of those coordinates to value not equal to 2, I have gotten a parallelogram. And what is the rank of this matrix? The rank of the matrix is basically 2 because the determinant is non-zero here. The determinant is 4. Therefore, the rank is 2 in this case. And rank is 2 implies there is information along two different directions. One along the coordinate 1, 1, or the 2, 2 coordinate, the first column, and the other one is along the y-axis. So whenever I tell that the rank of a matrix is n, it simply means that I have information in n different directions. That means to say that I have n variables which I need to look for. Especially when you talk about your machine learning and stuff, when I say the rank is n, suppose I have a 512 cross 512 matrix, and I say that the rank of this matrix corresponds to, let us say, 100. It means I have, of the 512 variables that I have looked at, I need only 100 variables. The rest 412 variables, whatever information conveyed by those 412 variables have been conveyed by these 100 variables, which means these are the key variables that we look for. Is that clear? For example, suppose if you were to be given an offer for a particular job, what is it that the job asks, your company asks for? The company asks for your experience, your qualification, your marks in your qualification, the salary that you earn, right? And the skill set that you possess. They don't ask you how much marks you scored in physics in class 12, nor do they ask whether you know to drive a car. If all these things have been put as a variable, they will all become immaterial. Is this clear? Therefore, this rank is extremely important number associated with any matrix. It is more or less like our mobile number. Everybody knows people by their mobile number now. So the same way, most of us must know the one number which would characterize a matrix or a transformation is basically its rank. Is this okay?
I'll just add to this. Yeah, so
Yeah,
you can kind of see this matrix, right? 2, 2, 0, 0.1. So what you see is that most of the information is lying along this particular axis, while the amount of information along this axis is lesser. So what we are mainly looking for is the kind of direction along which we maximize the amount of information which is there, and we can reject that particular dimension which is not very relevant to us. So what if we have data which is projected along this matrix, all we have to look at is at this direction. So all we have to do is project our data along this direction, so that we have actually reduce the amount of dimensions by 1. So actually, if you see here, this matrix has a non-zero determinant. So it is a full rank matrix. But what we notice is that most of the information is along one direction. So because of that, we only have to look at one dimension to make our basically our algorithm. We do not have to look at everything else. And in fact, this is the main crux of subspace methods, where we find the direction along which we maximize the information, and we try to reject those directions which we do not have to, because that will end up reducing our computation. In fact, for most matrices, you will have known that the algorithms might be in the order of n square or n cube. So by reducing the dimension by a factor of by 1, even by a simple factor of 1, we reduce the computational workload by quite a large margin.
The best example for this is any researcher for that matter, you take, we will put some 150 reference papers in our thesis, right? How many of us would have actually gone through all those 150 papers? At the maximum, we would have gone through some 30 papers. The rest 120 papers are basically for us to say, look, I have done so many things, I have looked at all references, and then I have come to a conclusion in this problem. But all the problem that you would have solved is basically taking a leaf out of these 30 papers. Is that clear? So it's basically that. Your rank tells you what are all how many vital directions are there in which you need to look at. Is this clear? In this case, in this particular case, there is another interesting stuff. The one that you see right now on the screen, you see that the matrix is still rank 2 matrix. It's an invertible matrix, but the effect of the second variable is very, very less. The second variable, the direction, if you see that magnitude is it's very small, which means that the second variable may not contribute effectively, but it is still an important fellow. Because if you make that instead of 0.1, if you make it 0, then you lose your complete stuff. You lose your information. It becomes rank 1. Are you guys getting this? Is that clear? So, as Sahil mentioned very clearly, that our aim, especially in terms of ML or whatever that we do, is to reduce the computations, because we have huge volumes of data. You cannot look at data sample by sample and then work. At the same time, you cannot put all the samples and then do a computation on that and work, because our computational resources, you have to use your computational resources effectively. Therefore, one way of doing that is, it's like how we say in life, reduce your wants. Life is beautiful. So reduce your dimension. Things will work well. At least those which can be visually perceived, that will work well. Maybe in audio you will have some issues, and in medical it could be a different ballgame. But as far as your images and things are concerned, you can still work with the lower dimension data and get almost accurate information that you really had. Especially, we're going to look at image reconstruction from SVD and things. We will see that what is happening. Okay. And there are quite a few questions in the chat box which is asking what is the tool that you're using. This is basically Python. And 3x3, somebody asked, we will be doing 3x3, but right now what we're doing is we want to tell everything about 2x2, and then we're going to move to 3x3. Is that okay? Okay. The next thing that we're going to do is,
should I explain these special matrices, or
you can do that. You can do that. Yeah, go ahead.
Okay, so I'll just explain some special matrices. So this is the shearing. So this particular shearing matrix, what you notice is that it shears along the x-axis. So basically,
Sahil, one small thing. Can you just change the matrix to 1 0 2 1 or something like that? You use unit matrix only. Yeah, and then make this 1 0 2 1.
1 0 2 1, right?
Yeah.
Okay. Yeah.
Oh, no. Okay, this is also fine. No, why I said was we'll go from the unit matrix, or it is 1 1 0 1. Yeah, that's also fine.
Okay.
Okay. Now, if you look at this is something which we very regularly do. This matrix that you see here is very, very important matrix which we always do, especially when we do word processing and stuff. This matrix is the shear matrix. And shear matrix is the matrix which is useful in doing font italicizing. You put in Microsoft Word, right? You highlight a letter and then say, or a word and then say italics. When you do that, this is exactly what happens. So the matrix which helps you do that is basically this shear matrix. Sahil, you want to say something?
Nothing else. This is sharing along x-axis.
Yeah, this is shear along x-axis, which means one of them is fixed and the second coordinate basically changes. Okay.
Scale, I think, is obvious. It's just
Scaling is basically that we know. So each side is getting scaled. The most important matrix that we're going to see now is what we call as the rotation matrix. We'll take the unit square, Sahil, and then see what's happening. Sahil?
Yeah, I'll just
make it unit square. Yeah. You just make it 1001.
Oh, okay. I'll put it as 0 for now.
Yeah. And then we'll look at all the rotation by various angles. So basically, this is unit square. Now you see what is happening. Can you rotate it by 45 degrees, Sahil? So rotation by 45 degrees is basically seeing that what's happening in rotation by 45 degrees. Your x-axis that you had as 1, 0 will now move along the 45 degrees line. The y-axis which you had it as 0, 1 will move along the 135 degrees line. That's what Sahil is now showing by the arrow. Is this clear? Now, what is the determinant of this matrix? So that's exactly why you see that 0.71, 0.71, minus 0.71 and 0.71. This 0.71 and 0.71 correspond to 1 by root 2, 1 by root 2, which corresponds to your sine 45, cos 45, or cos 45 and sine 45.
E power I.
Yeah.
E to the power I. Sine theta plus I cos theta plus I theta.
Yeah. So that is what you get. And what is interesting to see here is, can someone tell me what is the area of this thing? Can someone tell me what is the area of this? It is 1 by root 2 into 1 by root 2 minus of 1 by root 2 minus 1 by root 2 into 1 by root 2. So the area is still 1. The area is still unit area, but just that you have basically moved from the xy axis to a new set of axes. You see all the dotted lines here, that corresponds to the new axis that you get out of rotating by 45 degrees. Is this clear? Now, we will take a separate matrix. Sahil, can you do 1, 2, 2, 1? First column is 1, 2, second column is 2, 1.
1 second.
You make it 0. Yeah, angle 0, 1, 2, 2, 1. So now let's look at this matrix 1, 2, 2, 1. Can someone tell me what is the area of this parallelogram? That's equal to the determinant. Can someone tell me what is the area of this parallelogram? Determinant. Determinant is not the same. Can you please tell me what is the determinant? It is 1 into 1 minus 2 into 2, which is minus 3. Yeah. Oh, now we have landed in trouble. What is that? We said determinant corresponds to area of a parallelogram, and now you see that the area of the parallelogram is negative. Immediately what we'll do, if we were school students, we will rub that negative number as a negative sign and say, look, the area of the parallelogram is 3. But that's not what we do, because we cannot do what we do in school now. So area of parallelogram is minus 3. What does that minus indicate? Is the question clear? What does that negative sign indicate? Anybody? Are you guys able to understand what we are saying? Is everybody able to get? Can someone respond, please? Because I'm not sure if we are able to understand, because we are showing some graphs and then visualizations so that we drive home the points. But unless you tell us that if you are able to understand or not, it becomes difficult.
Sir, they are writing on the chart box, sir, because they
Okay, fine. Yeah.
They have mute status.
Yes. Sure. No problem. Yeah. So in this case, why is this area becoming negative? Oh, the area is becoming negative for some reason. What is the reason? The reason is, you see, we had 1001 was the unit square. If we go in the counterclockwise direction, then the angles will be positive. Now we are going in the clockwise direction. Where did 10 move? 10 moved to 12. 10 moved to 12, and our 01 moved to 21. You see that 01 axis has moved to 21, which is what Sahil is basically showing now with the arrow. I mean, with the cursor. Can you just move down to the origin, Sahil, with that line, along that line? Yeah. So that is basically your 2, 1. So your 1, 0 has actually, yeah. So there is a clockwise movement, and therefore that rotation by clockwise is what is contributing to this negative area. Is this clear? Okay. Sahil, can we move on to Kramer's rule? Yeah, and then we'll come back to eigenvalues and eigenvectors. Okay. Now, there is one more thing that we always study in linear algebra, which is Kramer's rule for solving system of equation. So if you have a system of equation Ax equal to b, what we do is to solve the first component of x. What we do, we replace the first column of A with B, and then take the determinant divided by the determinant of the matrix A. Sahil, I'll just I'll see if I can share the screen. Okay.
Should I stop sharing? I think I have to stop sharing on mine.
No, just let me see if I can do it. I think you may have to stop, is it?
I think I'll have to stop. I'll just stop it for once.
Oh, no, I think it works with my notes. So let me see. My screen visible to everybody?
Yes, sir.
Yeah. So now what we are doing is, suppose I want to solve this 2, 1, 1, 2 into x1, x2 is equal to 3, 3. Now, what does Kramer's rule say? Kramer's rule says finding x1, you replace the first column of A with 3, 3, the right side column that you have, and you retain the second column. You take the determinant of this, divide by the determinant of this matrix, 2, 1, 1, 2. Similarly, to do x2, what you do is you take the determinant of this matrix 2, 1, 3, 3, divided by the determinant of this matrix 2, 1, 1, 2. Now, in essence, what you're saying, this is a determinant and this is another determinant. So what we see is basically telling you that x1 is the amount of variation that you have had because of changing its coordinate this way. So what is the area change that you have? This is area with 3, and this is area with 1, 2, 2, 1. Okay. So the ratio of this is going to give me the value of x1. Similarly, the ratio of these two areas is going to give me the value of x2, which means how much is the area scaled? The area with 2, 1 gets scaled by x1. That is equal to the area that you with 3, 3. That's exactly what we are going to see in. Sahil, you can take over. I hope it is fine. Like we keep changing our screens and then I explain and then he does. I hope it's not causing any kind of distractions to you all.
Okay, so we can continue with this Kramer's rule then. Yeah.
So if you see here, we are again taking that matrix 2, 1, 1, 2. Oh, that's brilliant. What is the right hand side he has taken? The right hand side he has taken is 1, 0. That means he's going to solve the equation 2x1 plus x2 is equal to 1 and x1 plus 2x2 is equal to 0. So he's trying to figure out what is the value of x1, x2. Sahil, you can explain now.
Yeah. So first we start off with the determinant of the original matrix. So that will basically be the transformation by the unit square. So 2, 1, 1, 2 has a positive determinant of 3 because like I think Sir explained just now, that clockwise rule and anti-clockwise rule, right? So basically 2, 1 is the first vector, that is the vector 1, 0 being transformed by the matrix. That becomes 2, 1. So that is 2, 1. 1, 2 would be this matrix. So when you take the right hand rule, you can see that it's clockwise direction. The direction is anti-clockwise. So when you take the right hand rule, the vector points outward, so z axis. So because of that, the determinant is positive and it is 3. Now what do we do with Kramer's rule? First, we substitute the vector b, which is the one which we want to find out, in here. So the first vector from 2, 1, it becomes 1, 0. So here you see 1, 0 and 1, 2. So 1, 0 and 1, 2 is basically represented by 1, 0, 1, 0 and 1, 2. So this purple color, purple, what do you see here? Purple is representation. Yeah, parallelogram is the representation of the matrix A1, and you see that it also has a non-zero area. So since it has a non-zero area, basically what we can calculate is find the determinant of it, And since we see that the anti-clockwise rule is followed, the determinant is positive. So we get an area. We see that the base is 1, height is 2. So the area is 2. So by the Cramer's rule, the first value, the first component of x is basically 2 divided by 3, which is equal to 0.67. So, and the second component is basically represented by matrix A2, where we substitute the second column by the vector 1, 0. This is represented by the blue color parallelogram. And in this blue color parallelogram, you see that it's transformed anti-clockwise. So 2, 1 is this particular vector, and 1, 0 is this particular vector. So the vectors will change in the clockwise direction. This implies that the determinant is negative, and from area is equal to base into height, we can see that the area is 1. So our final value for the second coordinate of x is minus 1 by 3, which is equal to minus 0.33.
So what it basically says is the area, if you take this original matrix 2, 1, 1, 2, and if you want to look at this 1 and 0, you see that the original area gets scaled by a value of 0.66 when you replace the first column with that value 1, 0, and it changes by a value minus 0.33 with the orientation change when you substitute the value minus 0.3. Is this clear? So basically what we have done, we have tried to solve the system of equations by basically looking at the ratio of two areas. Is this okay? And what is interesting is, suppose even if one of them is 0, let's basically put, Sahil, can you change the second column first coordinate to 1, 2, right? So 4, 2, can change it to 4, 2? Change it to 4, 2. Now you see what's happening.
The determinant falls to 0.
The determinant falls to 0, but that doesn't show up. Sahil,
No, it cannot show, right? It will be the area.
That line I have to see. Yeah, that I have to see the line. No?
Oh, okay. No, that I'm not showing it right now purposely.
Okay, fine. So it basically shows that the okay. Now let's look at the let's look at the two parallelograms.
I'll show it here itself.
Yeah, sure. Cramer's rule only just. Yeah.
I'll show it in this.
Sure. 2, 1, 4, 2. So now you see that the parallelogram has become a line. Whatever value of B you put now, it is going to be a problem because your determinant is 0. The matrix is not invertible. Therefore, ratio of areas cannot happen in this case. Worst case, it could only be ratio of two lines. Is this okay? Now, the third thing that we are going to see is we are going to see what is the meaning of an inverse of a matrix. So that also we should know, because we are looking at geometric perspective. We must also know what it is to say inverse of a matrix. If a matrix if a 2 cross 2 matrix has two different columns, then we say that the columns basically enclose a parallelogram. Now, what is it to say if I have A inverse? So let us see what A inverse is. Let's basically take the same matrix 2, 1, 1, 2, and then see what is the inverse for that matrix. Go ahead, Sahil.
Yeah. So here we see that the original matrix is again 2, 1, 1, 2, which is represented by the gray color parallelogram. Then what we do, we generate.
Sahil, can you just rotate it and keep it in normal? Can you just rotate it a bit? Yeah, so that this is fine.
Okay. Yeah. So here we can see that this matrix scales the unit square by this gray color. The result would be this gray color parallelogram. Then we look at the adjoint of a matrix. So the adjoint of a matrix is what we use to calculate the inverse, right? That is, basically the transpose of the.
We basically change the coordinates of your diagonal. We change the diagonal coordinates, and the off diagonal elements signs are changed. In this case, the diagonal elements are the same, therefore you don't see the change, and the off diagonal elements are basically -1 and -1. Therefore, you see the parallelogram has now shifted. What you saw on the right hand side is now shifted to left hand side, if you actually see. Okay. That is the adjoint of A. Adjoint of A is basically a matrix. And what is determinant of A? Adjoint of A is scaled by the determinant value. The inverse of a matrix is adjoint A by determinant A. And therefore, when you scale it, whatever green color or a blue color small parallelogram that you see, that would correspond to your inverse. Is this okay? Is everybody able to get this? Is everybody able to understand the meaning of inverse, geometric meaning of inverse, geometric meaning of adjoint and stuff. You have any questions? Because after this, I'm going to, we'll be getting on to eigenvalues and eigenvectors in 2 dimension, and then we'll go to 3 dimension, and then we'll do SPD. So I really want to quickly see if there are any questions in 2 dimension till now what we have done. You can unmute and ask. Any questions? No questions? Okay.
There are no questions from the part.
Yeah, if there are no questions, we'll go ahead. Sahil, can we go to the eigenvalues and eigenvectors in 2D?
Yeah. So here we can display the eigenvalues.
Yeah. See, this matrix, this instead of this one, you also see for a 2, 1, 1, 2 matrix, there are 2 eigenvalues and eigenvectors which are displayed over there. 1, 1, 2, you know, why is it showing? Okay, eigenvector, that's normalized eigenvector. Okay, fine.
Yeah, these are normalized.
Yeah. So what you see is the eigenvalue corresponding to this matrix 2, 1, 1, 2 is basically 3 and 1. There are 2 eigenvalues here. You try to solve the characteristic equation, which is lambda square minus 3 lambda plus 4. That is equal, lambda square minus 4 lambda plus 3 is equal to 0. So you get lambda is equal to 3 and lambda is equal to 1. And therefore, the corresponding eigenvectors are basically 1, 1 and 1 minus 1. That's exactly what we did today in the class. You remember, we said that this matrix 2, 1, 1, 2 is the mother matrix or mother transformation. And we said that 1, 1 is that violent kid. That is the eigenvector. And we said that the 1 minus 1 kid is the usual normal, very humble kid. So that's exactly what we see here. The 2 dark lines that you see here in this particular graph are basically the eigen directions. These 2 are invariant directions. Is this clear? This the line that you see on the right hand side corresponds to the vector 3, 3, and the one that you see on the left hand side corresponds to the line minus 1, 1. Yeah, that corresponds to the line minus 1, 1. It's on the direction of minus 1, 1. So whatever that you try to do on this 3, 3 vector will continue to be there along 3, 3 vector. It won't go anywhere. And that's exactly why we say for this matrix, 1, 1 is basically an invariant direction. This is invariant direction. Where do we use this eigenvalues, eigenvectors? I'm quite sure most of you are working with ML, and you must know that there are certain things called eigenfeatures and stuff, which are invariant, like your iris, your thumbprint, your earlobes, and all those things, like what they take in Aadhaar card. These are invariant features, and they are unique to a particular person. So we must know that for a matrix, eigenvalues and eigenvectors are unique. Suppose if I tell you that this is the eigenvalue, I can fix any matrix to have that eigenvalue. But if I tell you that this is the eigenvalue and the corresponding eigenvectors, then there is only one matrix which has that. Is that clear? So that is what we see here. But there is a problem with this. What is the problem? Let's take this matrix 0, 1, minus 1, 0. Can you take that sign? Change the matrix to 0, 1. First column is 0, 1. Second column is minus 0. Yeah, fine. If you look at this, there is something interesting happening here. What is this happening? This fellow says the eigenvalue corresponding to this particular matrix. You see what this matrix does in the first place? The matrix does a rotation by, what is the amount it rotates by? 270 degrees. Is that right?
Yes, sir, continue.
It's a 270 degrees rotation matrix, and therefore, if you look at the characteristic equation of this, you will get lambda squared plus 1 is equal to 0, which means lambda would be equal to plus or minus j. That's exactly what you see here, whatever Sahil shows, which means I have taken a real matrix 2 cross 2 matrix, but I ended up getting a complex eigenvector. I cannot represent complex fellows in real field. Therefore, what we conclude is rotation matrices in 2 dimension do not have real eigenvectors. They don't even have real eigenvalues. Of course, that is naturally expected because a rotation matrix, the job of rotation matrix is to rotate any vector, and therefore it cannot have any invariant direction. Is this clear? Therefore, one thing we must know is it is not just with respect to 2 cross 2 matrix. It is any matrix whose directions, whose dimension is even number, 2n cross 2n. If you take a matrix 4 cross 4, 6 cross 6, 8 cross 8, 2 cross 2, 10 cross 10, 1000 cross 1000, any such matrix you take, you can there will be a situation where you will end up getting all the eigenvectors to be, all the eigenvalues to be complex conjugate pairs, which means we will not get real eigenvalues in that case. This is one particular thing that you have, which you will not find in a odd dimension matrix. Suppose you go to a 3 cross 3 matrix, you are assured that there is at least one real eigenvalue or eigenvector. Is this clear? This is fine. Shall we go? Sahil, can you just do a 1 0 0 0 projection matrix and we'll show the eigenvalue for that, eigenvectors for that? Oh.
Yeah, singular.
Yeah. So in this case, the matrix is basically 1 0 0 0. That means it is a rank 1 matrix. The only direction that you have is your 1 0 direction, and that is actually the eigen direction, which means all it says is if you are projected onto the x-axis, there is no way you can come out of your x-axis. You will continue to walk only along the x-axis. This is exactly what we are going to say even in case of SVD when we do, or PCA that we do. Like Sahil told in the first place, where we took the matrix 2 1 and 0.1. When we took that matrix, he said that look, 0.1 is very small compared to 2 1. Therefore, all the information is available on the vector 2 1 in the direction of 2 1. So that's exactly what you're going to say here. The moment you do projection, you are going to lose some information. That's exactly what we are going to do in SVD and PCA. We are going to take a higher dimensional matrix or whatever and then project it to a lower dimensional vector space or a lower dimensional space. And what we are going to claim is, even if you project it into a lower dimensional space, you are not going to lose much of an information because most of the information is available here. This is something similar to your discrete cosine transform. When you do discrete cosine transform and you try to, basically when you do discrete cosine transform, the first few coefficients are enough to get back to retrieve your, what do you call it, to image or whatever when you do DCT. I'm quite sure all of you would have done, because most of the energy compaction happens in the lower frequencies. The same way here, most of the information are available in the dominant, in the direction corresponding to the dominant eigenvalue. Okay. Now, can we go to the 3-dimension, Sahil? Are you all able to can someone unmute and tell that if this exercise is fine, that you are able to understand, you're able to get some clear concepts? Otherwise, it would, I mean, you shouldn't feel it a waste of time sitting and saying what's happening. Can someone tell me, unmute yourself and tell me if this session is useful to you all? Are you getting some insights? Yeah?
Check the chats, I think.
Yeah, I just checked. Okay, fine. Yeah, okay. Now let's go to 3-dimension. Somebody asked what is happening with 3-dimension. Can you show visualizations in 3-dimension? Yeah? But in 3 cross 3, how the values are plotted. You see this. This is exactly what he has done in 3 cross 3. He has taken the matrix 2 0 0 2 0 0 0 2 0 0 0 2. So in this case, in 3-dimension, it won't be a unit square. It will be a unit cube, because I'm going to add the height dimension also. Therefore, I'm going to have a unit cube, which is that solid cube that you see. Show it in 3D itself, Sahil. Yeah. So you see that the center of that entire gray color stuff that you see box, that is basically the unit cube that you have. Is this clear? Now that unit cube is basically scaled by 2. So now you have to get a 2 by 2 by 2. Okay, you have a volume, you have a cube of volume 8. Now what is interesting is, in 3-dimension, the determinant of a matrix is equal to the volume of the parallelepiped. Like how we said area of parallelogram for determinant of A. Now what we are saying is determinant of a 3 cross 3 matrix is basically your volume of parallelepiped. All the other things will work in the same way like what we are doing. All other things that we have taken will work exactly like what we did in 2-dimension, except for the fact that in 2-dimension, I may or may not have real eigenvalues, but in 3-dimension, I'm guaranteed at least one real eigenvalue will be there, because you have a lambda cube. Any lambda power 2n plus 1 will ensure that I'll get at least one real eigenvalue. Rest of them could be complex conjugate fellows. Okay. And let us see in this case, like again Cramer's rule will be equivalent to saying, look, for Cramer's rule, what I'm going to do is I'm going to look at change in volume divided by the original volume. Can we just do that, Sahil? Yeah.
So this will be your first. Let's assume that the vector we want to find for is 1, 1, 0. So first we substitute the first column by 1, 1, 0. That is done here, and the rest are the same. So when we display it, we see that these two y-axis and the z-axis will remain the same, but the x-axis gets transformed to this line. That is 1, 1, 1, 1, 0. And we see that this is a full rank, is full rank, and we find that the volume is equal to 4. So we find that by Cramer's rule, the first coordinate of the x is equal to 1 by 2, that is 0.5.
Similarly, you can find the second coordinate and third coordinate. And what you see interesting is this. See, after you have made it 2, 0, 0, or after you changed it to 1, 1, 0, 0, 2, 0, and 0, 0, 2, you see all of them are basically planes passing through the origin. Right?
These are basically these are basically the coordinate planes. So each of the coordinates.
So, these are go ahead, sir. Go ahead.
Yeah. So basically, these green color coordinate lines are the main coordinate planes. So green is basically XZ, the YZ plane. Blue is the XZ plane, and red color is your XY plane. So these particular solid planes or the transparent planes are basically the transformation of each of these planes by this particular matrix. I think
matrix.
That maybe we should have
exactly.
Yeah.
Now, see something interesting happening here. In two-dimensional, suppose can you just change, Sahil, can you change the first column to 0 to 0? Change the first column to 0 to 0. Same as the second column. That's fine. Second, no. Yeah, you made it one of them to be 0, right?
Yeah, 0 to 0. I mean, you wanted unit. You wanted a unit, right? Is it?
I want the first column to be 0 to 0. Second column also to be 0 to 0. First and second column the same.
Yeah.
Oh, fine. This makes sense. Now this is also fine. Okay. Now, what is it that we are seeing here? If you see, the determinant of this matrix is 0 because there is one column which is completely 0. So the determinant is 0. Therefore, the volume is 0. What is interesting is now the parallelepiped has become a degenerate. It has degenerated to a parallelogram. So whatever I get, I say I'm going to look at the area of the parallelogram. And this is exactly what we mean that when we say the rank of a 3x3 matrix is 2. When we say rank is 2, what do we mean by rank is 2? When we say rank is 2, we mean to say that there is a 2x2 invertible matrix that I can find within a given matrix. Right? And therefore, the information is there in the 2 dimension. And that's exactly what we meant by saying our rank. Is this clear? So wherever there is a solid geometry that is formed, that corresponds to an invertible space. Is this clear? In this case, there is a 2-dimensional. There is the information that you want is available. Though the data you have collected is in 3 dimensions, the information that you want is available only in 2 dimensions. That's what it means. And interestingly, here also you will see that since it makes a parallelogram, I will say that there are 2 vectors in 2 different directions. And therefore, these 2 vectors are linearly independent. The moment you have 2 linearly independent vectors, I will always have an area to be coming into picture. If you are going to have it in 2 dimensions, I'm going to have an invertible matrix. If you're going to have a 3-dimensional matrix, I will not have an invertible 3x3 matrix, but I will find a small invertible 2x2 matrix in that. Is that okay? Go ahead, sir. Okay. You don't do Cramer's rule in this. Let's not do inverse also. Let's go to Gram-Schmidt.
Okay.
This is another important thing which we must know. What is Gram-Schmidt? Somebody asked me in the morning, what do you mean by orthogonal basis function or orthonormal basis? So what is this orthogonal basis? See, you must remember that whenever you take a matrix, the basis corresponds to a set of linearly independent columns that you have. I mean, as far as your column space is concerned, the basis of the column space is nothing but the set of linearly independent columns that you have. But the linearly independent columns means the columns are not orthogonal, need not be orthogonal. The columns will be at some angle, but that actually makes sense. It being at some different angle, it still makes sense. But the problem with this angle being, the angle between 2 columns being not equal to 0 I mean not equal to 90 degrees, it comes with a problem. It comes with an issue. What is that? It is going to disfigure any shape that you give. You give any input, it is going to disfigure it. For example, when you took the 2 cross 2 matrix, 2 1 1 2, what did it basically do? It basically sheared that matrix 1001, that unit matrix that you had. It basically sheared that, and you ended up getting a parallelogram. What was a square became a parallelogram. It became an oblique figure. So if you give a circle as an input to this 2112 matrix, you will end up getting an ellipse. So it disfigures. Whereas if you have an orthogonal matrix with orthonormal columns, then the shape will be preserved. Is this clear? If you look at discrete Fourier transform, if anybody has done it, you will see that the columns of the discrete Fourier transform, they are orthonormal to each other, and it preserves whatever information. So basically, it preserves the shape, it preserves your length, it preserves area, it preserves volume, everything it does. Is that clear? So how do we generate orthogonal vectors from Gram-Schmidt? That's a very simple procedure. Yes, Sahil.
Okay, I'll just go towards. Yeah, so here I'll just animate this. So here we see that the vectors that we've given are actually not orthogonal. So we see that the first two vectors, this is 1 0 0, and the second one is 2 2 0. So there is an angle between them. The angle is 45 degrees. And then if you see the other two vectors, this is 3 3 3 and 2 2 0. So we see that there is another angle between them. Now basically what we want to do is find an orthogonal, we want to find the set of orthonormal bases which span the same space as an orthogonal ordered basis. So what an orthogonal ordered basis would be, such that each of the vectors which are there are orthogonal to each other. We are not specifically specifying the condition that each of them are unit vectors, which means they're not orthonormal, but they are orthogonal. And the second thing is, now we want to basically create a set of orthogonal vectors out of these particular vectors. So this procedure has a lot of uses in machine learning as well. So I'll just show you how this is specifically being done. So if you've heard of the Gram-Schmidt process, basically what you do is you first choose the vector v1 as the same as the first vector, that is u1. So that's what's being done here. So v1 is equal to u1. So this is your first vector in your set of ordered orthogonal vectors. Your second vector, which is v2, is basically the vector u2 from which the component along u1 has been subtracted. So basically, you take this u2, you project it along v1. So that will basically give you the component of u2 along v1. Then you subtract that component from u2. So when I animate it, so you see that basically what is happening now is, you can see that the vector component. So basically what is happening is the projection of u2 along v1 is being subtracted from u2. So you see that u2 is slowly becoming orthogonal to v1. So here you see. So basically this is u2, that is 0 2 0, while v1 is this 1 0 0. So from u1 and u2 we basically generated two orthogonal vectors, and such that v1 is equal to u1 and u2 is basically the component of u2 subtracted from which the component along v1 has been subtracted. Now let's proceed. So here we see this is u3, but this is v2 and v3. Now we see that there is an actual component of v3 along both of u3 along both v1 and v2. First we subtract the component of u3 along v1. So let's show that. So here we see that we are slowly subtracting the component of u3 along v1. So now we are left with u3, which is this, minus the component along v1. So these two are actually perpendicular to each other. So they're orthogonal. Now, then we basically subtract the component of u3 from the component along v2. So finally what we are left with is v1, v2 and v3, which are basically generated from this set u1, u2 and u3. So these form an orthogonal basis. and we see that any if angle between any of them is 90 degrees.
And what is interesting to see is that these three vectors that you get v1, v2, v3, they will span the same space that is spanned by u1, u2, u3. Except that now you have got back exactly what you had. I mean, when it was v1, v2, v3, I mean u1, u2, u3, the axes were all oblique to each other. The moment you have an oblique axis, the information gets completely skewed. Whatever input information that you give, it gets completely skewed under that transformation. So what you do is you convert that to an orthogonal basis and then represent it in orthogonal basis, which means the information doesn't get skewed anymore. The information is preserved. Is this okay? Sahil, can you go ahead?
So shall I go move over to SVD?
Yeah, we'll tell about SVD, like what is happening in terms of graphical, and then we'll take the code and then do the this one. Okay.
Sure. I'll just take the matrix.
Are there any questions or any comments that you have? Is there something that you want us to do a bit more and then explain? Till whatever we have done, is everybody clear with it?
They mentioned in chart box they are getting. Yes.
Yeah, I'm just checking that. Yeah, sure.
So we can proceed, I think, because you're
Yeah, let's go with SVD. Yeah.
Okay. So SVD, have you taught that, sir?
No, I just gave them what SVD is. I said that if you have a rectangular matrix, then you cannot do eigen decomposition, so you have to do SVD. I haven't told them what it is. Now I'll explain it from here. Okay. See,
Okay.
the thing with a rectangular matrix, any m cross n matrix, is that there is towards the end of our discussion in the morning session, I told that if you have a real symmetric matrix with distinct eigenvalues, the eigenvectors are all orthogonal to each other, which means now I'm in a position to get an orthogonal basis for that particular transformation. But if I get a rectangular matrix, it is impossible for me to find the eigenvalues and eigenvectors for that. It is very, very difficult because it's not even defined. It's a rectangular matrix for which, first of all, I need to define a determinant, which is not done. The determinant for rectangular matrix is not defined, and therefore I have to do something which should help me get a rectangular matrix, square matrix from this rectangular matrix. So what I do, I can do this. Either I can take A transpose A, or I can do AA transpose. The moment I do this A transpose A or AA transpose, I get a rectangular matrix. Now what is happening is, a square matrix. I'll just share my whiteboard for a moment. You don't, you don't unshare it. You just leave it like that. Okay. I'll just see if I can. Oh, it means it will stop. Okay, fine. I'll do that. Okay. Now, so let's look at this SVD for a moment. So what am I going to have? I'm going to have a matrix. I hope my screen is visible to all. A
Yes.
m cross n. This is a rectangular matrix. Let us say, assume the rank is n. Assume rank is equal to n. This is very bad. Just a minute. I'll probably share my screen rather than this. This is okay. Now what I do is I look at this matrix A m cross n, and a rank of this matrix is n, which means, and let us say m is greater than n. This simply means A is a full rank matrix. Now, what I'm going to do is I'm going to look at A transpose A. Transpose A is a n cross n matrix, and the rank of A transpose A is also equal to n. Rank is equal to n. Now, since this is a square matrix, I can start looking at eigenvalues and eigenvectors for this. So A transpose AX is equal to lambda x I can find. Is this clear? Let us call this C. So what I'm going to do is I'm going to do a very, I should not say, I'm going to do a very loose comparison with something else now, and then going to bring you the idea of singular values. So suppose I have a vector x, which is, let's say, x1, x2. What is x dot x? X dot x is nothing but x transpose x. which is nothing but x1 square plus x2 square. This is basically saying this is the squared length of x. Is that right? X transpose x is basically squared length of x. I'm seeing A transpose AX equal to lambda x, but what I'm looking for, what was AX? So what I do is I use this abuse. I mean, I'm going to use abuse of. I'm going to do abuse of concepts. I'm going to do abuse of all convention held and all. But I just want to drive home this point. This is therefore equivalent to, since it is X transpose X is square term, this is equivalent to. This is not A square, but this is equivalent to A square. Can I tell that? Equivalent to A square, because X transpose X is X square. Can I tell this? Therefore, what is this? Ax will be equal to lambda x. I'll put it this way. Okay. Again, I am just as I very clearly mentioned, I am going to do some abuse of notation and concepts. Notation, concepts, everything. But I'm trying to draw a parallel between this and this. So this square root of lambda, basically these are positive square root of lambda. These are what we call as singular values. And we remember we had this. What was that? A, the matrix A was equal to V sigma U transpose. What we had. We said this can be decomposed into V sigma U transpose. Therefore, what you see is this U are basically the eigenvectors corresponding to A transpose A of A transpose A. We call it as the right eigenvectors, and V will become the left eigenvectors of A transpose A, or A. You can get that, okay? And this matrix that we said, which contains all the singular values along the diagonals, which corresponds to the number of rows R, these fellows are basically my singular values. Is that clear? Now, what is the advantage of this? As I said, you can compute what is called as A pseudo inverse from your singular value decomposition. That's one important and interesting observation that we have. And this is used for solving many problems. Now we will see the geometrical meaning of SVD. What is actually happening? Okay, we'll see what is geometrically SVD all about. Go ahead.
So I'll just explain it in brief. So basically, what we are doing in SVD is what you see with U sigma and V transposes. Basically, V represents the. I'll just start sharing my screen once again.
Yeah.
So V represents basically the row space of the row space. So basically, what we find is that V is an orthogonal basis for the row space. So all the rows are represented by an orthogonal basis given by V. So when we say U sigma V transpose, since V is an orthogonal matrix, V transpose will be its inverse. So basically, we are taking any vector that's lying in the row space, we are inverting it. So what does that inversion do? I'll show you in this video. So what you see, so what you're actually seeing is that the vectors that are corresponding to V, the orthogonal basis which is spanned by V, it is basically getting inverted. So that means all the vectors which are there as the columns of V are going to become the XYZ axis. And then we have sigma. Sigma is basically an identity, basically the value of singular values, which is basically like a diagonal matrix, and each of these diagonal entries correspond to the singular values. So what they particularly do is that they scale. So when you see, they actually get scaled. So that's the X, Y, and Z axis getting scaled. So till now, what you've tracked, you've seen that every vector that's along the row space is getting pushed back to the X, Y, Z axis. It's then getting scaled by this sigma matrix, and then finally it gets shifted by this U matrix, which is basically the column space. So I think Sir would have taught you, right? Like any vector that's there in the row space of a matrix will get pushed to the column space of the matrix. So in that sense. So what you see is here you see is that finally, what is happening is we take any vector that's on the row space, we take the inverse of it so that that row space gets spanned instead by x, y, z. It gets scaled by these singular values, and finally it gets transformed into the column space by u. So that's the whole idea behind, in some sense, the idea behind SVD.
Sahil, I'll just take a minute of time. Okay.
Sure.
Yeah, I'll just share my screen and probably I'll tell them something more. The question is this. For example, let's just look at this. The moment I put 1, 1, I know what this matrix does to this vector. It says, look, I am scaling this particular vector by a value 3. I'm going to equally scale along the x direction and y direction. Suppose I put this vector 2, 1, 1, 2, and I put this 1, 2. This is going to give me 5. Now, this makes sense that this gets scaled by the amount 3 and the same vector comes out. This is like, I don't even know what is happening to this matrix. What is happening to this vector? Because the first value, excuse me, 4, we don't even know. It gets, this particular component gets scaled by 4. And this component that you get here, it gets scaled by 2.5, which means I'm going to have some unequal scaling. I really do not know what is even happening to the input vector that I give. It's like a cricketing shot that Dhoni plays. He closes his eyes and then hits the helicopter shot. Whatever ball comes, he is going to hit the helicopter shot. We don't even know what is actually happening with that. So if I want to know what exactly this 2, 1, 1, 2 matrix does on 1, 2 to get this 4, 5, that gives me more strength, or that gives me a strong grasp of fundamentals. So what I will do is I will basically express this as PDP inverse. I'll use PDP transpose because the eigenvectors corresponding to this eigenvalues 3 and 1, they are orthogonal. So I'll use PDP transpose. And this P matrix is an orthogonal matrix. So what I will say is, suppose I want to do, instead of AX, now what I want to do is I'll do PDP transpose X. Now, the moment I say P transpose X and the columns of P are all unit vectors, this P transpose X will correspond to projecting vector, projecting X onto the eigen directions. Once I do this projection, now what I do, I'm going to scale the projections. That's all, by this value, lambda 1, lambda 2, etc. So the effect of AX, if A is a real symmetric matrix with distinct eigenvalues, the effect of AX can be captured as sum of scaled projections, linear combination of projections onto orthogonal axis. This is what happens for a square matrix onto orthogonal axis. Now, best example is what? Best example is our standard unit identity matrix. You take this vector 4, 1 or 4, 3. It's nothing but with the vector 1, 0 in the direction of 1, 0 plus 4, 3 dot product of this with 0, 1 in the direction of 0, 1. So now I see that if I say 1, 0, 0, 1 into 4, 3, I simply know what it is. What is this? I know that the effect of this identity matrix onto 4, 3 vector is basically the sum of scaled projections onto these two directions. That is exactly what happens here. And that is exactly what you would see here in V sigma transpose also. Is this clear? Whereas this is meant for square rectangular matrices, or for that matter, any matrix M cross N. M could be equal to N also. Is this clear? So these two are equivalent, PDP transpose X or PDP inverse X, and your singular value transpose, decomposition, U sigma U, V sigma U transpose. These are in essence almost similar in the sense that this is an inverse matrix and that is a transpose matrix. When will the inverse of a matrix be transposed? Whenever the matrix is orthogonal. Therefore, U is an orthogonal matrix. This is a diagonal matrix. This is also a diagonal matrix, except that it is a rectangular matrix. This is an orthogonal matrix and matrix. V is an orthogonal matrix, except for the fact that there is only one matrix P which is going to diagonalize this matrix A. Here I'm going to use two different orthogonal matrices to diagonalize my matrix A. That's all. Is this clear? Now,
each of those matrices correspond to the row space and column space.
Column space ka basis. Okay. Now,
So
with
U
this,
is the row space, B is the column
is the
space.
column space. So with this, what is it to do SVD on images and how to retrieve images or reconstruct images with few, lower rank, few singular values. So how can we do it? So this is the original image, right, Sahil? Hello, Sahil. Sahil, can you hear us? Can you hear me?
Oh, I think I'd muted. Sorry.
Okay, fine. Go ahead. Yeah.
Yeah, sorry. Yeah. So okay. So I'll just briefly round this down. So we are going to try compressing this 500 by 500 image. So it's called flat.jpg. We come first. Initially, we import the image, and then we whiten the image. This is by subtracting the mean and dividing by standard deviation of all the values, so that we get a standard deviation of 1 and a mean of 0. Now, first we find the SVD of the particular uh, image. So an image is basically, you can think of it as a matrix itself.
See, this
And
is 1 minute, Sahil. This is exactly what you call as cleaning your data. You mean center it and then normalize it by using the standard deviation. This is what you call as mean center data in your normal machine learning parlance. Okay. Yeah.
Yeah. Okay. So then we find the SVD of the matrix. So SVD will give you two orthogonal matrices and one diagonal matrix. So now we can assume that the information, the number of bits here is 500 by 500. This will the two orthogonal matrices will also have 500 by 500. So 500 by 500 into 2, and the singular matrix is a diagonal matrix. So it's basically the length is 500. So currently the image basically has we can think of the image having 500 by 500 into 500 components. Now what we do, we try to compress the image by kind of reducing the number of dimensions, so number of vectors. So instead of taking all the vectors that is given by u sigma v transpose, we put the last 200 of them. Let's take the rate as 200. So we set the last 500 vectors. So if you've seen if you look more into SVD, you'll find that the singular values are arranged in the order of their magnitude. So the first eigenvalue will be very high, and the last eigenvalue will be the lowest. And because of this, we'll see that most of the information will be present in the first eigenvalue. I think in that 2D demo you have seen, right? The largest eigenvector is there, and there's a small eigenvector, and most of the information can be contained in that large eigenvector. So when we put eigenvalue,
corresponding to the eigenvector.
Corresponding to the largest eigenvalue. Yeah.
Yeah.
So it's in the same sense, the largest singular value will have the most information, while the last one will be the least. So first, let's see by what happens when we put the 200 of the least significant eigenvalues to 0. So I'll just run this image. Save file and run. You see that the image hasn't changed barely. I'll just show it you the actual image. You see that the image is barely changed. This is the original image. This is the new image. So
can you just put it side by side and then show it?
Yeah. So this is the original image, and this is the new image. So you see that this has maybe this little bit of dust here is not clearly seen, but the rest of the image is, to the human eye, is almost indistinguishable.
So the most of the features are now captured within the first 300 eigenvalues, singular values, or first 300 directions. You will see surprisingly that even you can reduce it further. Can you just reduce it?
Reduce to 100.
Yeah. So now what we have done is we have basically made use of this is rank 400. You're taking 400 singular values, right?
No, reduce. I'm taking only 100 singular values.
All the 400 are you making 0, is it?
Yeah.
Okay, fine. So now I'm just taking, he's taking 100 singular values, and you see what is the kind of information that you get. Let us compare these two images. The one, which is the
This is the one
original
on the
image.
right. Is that right?
That's the original image. The one on the left is your reconstructed image using only 100 singular values.
So only instead of 500 dimensions, you've scaled it by a massive amount, by 100. It's only 100 right now. And what we see is that certain details are lost at the main. If you could, maybe it's not that clear, but you see that there is a little bit of detail lost. But I think through the screen, from the screen sharing itself, you can see that there is barely any change. So through the visual eye, it's almost indistinguishable.
So can you further go down? So I'll say probably use only 50 singular values.
Yeah.
And probably we could even check the maximum of the singular value and minimum of the singular value. Then we'll get a rough idea.
So let's go to 50 next. After that, I'll keep reducing it further.
Yeah.
So the one on the right here is the original. One on the left is the new one. But here you see that finally some amount of detail is lost. There's some bit of noise that's coming in,
Yeah.
etc. But it is still kind of relatively
Perceivable. Yes.
Perceivable to a human eye.
So this means the reconstruction is done using only 50 directions. We were actually looking for 500 cross 500. We were looking at 500 cross 500 dimension. Whereas for this image, it looks like the reconstruction can be done with information what is available only in 50 dimensions or 50 different directions. Now he has probably done, what is the?
This is 5.
So basically he has done 5 now. He has taken only 5 singular values. You see now this is where the problem is. So 500 cross 500, you still have some information saying that, okay, it looks like a line. But then you see you cannot really clearly perceive it. Is that clear? All the details are lost. Is this okay?
So our whole idea is to reduce the amount of dimensions, and most of the information we found is in the lower dimensions.
That is exactly what PCA does. Curse of dimensionality reduction. All these things are your your PCA. Basically, it reduces your information to fewer dimensions and then still tries to make sense out of it. Is that okay? And what is more interesting as far as this, your singular value decomposition, that whatever we've been seeing right now. See this, you have from the general matrix theory, we know that the sum of eigenvalues is equal to trace of the matrix. That means the sum of diagonal elements. So what we see here is, if you have a very large eigenvalue divided by that sum, then that is going to contain the maximum information. That's what we call as our spectral theorem, or whatever in spectral theorem that you see. Basically, it says that the dominant eigenvalue divided by sum of eigenvalues, that contains the maximum 96% information. Can we just check what are the eigenvalues, singular values here? Can you just show the table or something? We'll just take the max and min. Min should be 0, but we'll just take max and non-zero min. Let's min is 0 for sure.
It will be somewhat near 0. All right, just see if I can print it.
Yeah, it should be available in the. It's there. No, S is equal. You click that 500 cross 500 S matrix.
Yeah, but it's 500 cross 500.
Yeah, that. Just click that. See, the maximum eigenvalue is 331.94. What is the next eigenvalue? Double click that. Can we just check the Excel sheet or something? What are that? Okay. It's not displaying.
Yeah, here you can see 331.
Then you go 213, 115, 100. The rest of them are all gone. All the other fellows are 0, which means your maximum information is there in that dominant eigendirection. Now you want to add one more dimension. Can you just make it 6? You've taken 5, right? First 5.
No, right now I've put only 5.
Oh, you made it 5. Yeah. Yeah, you just change it. Let's put some 200 dimensions or something like that and then check what's happening.
I'll just put you one. One second.
Now if you see, this is not that one. I think we have not got
There
the.
was some issue with the piping. Yeah.
Okay, fine. But I think this is not the. This only shows 5, right?
No, it will show.
Let me just close this.
Yeah, now it's showing 200. Yeah. Hello?
Yeah, I think we are not able to see that set of values. Now it's fine. You see again, you see the magnitude of your singular values. It starts with 331, and if you go further down, you should be having some values which are close to. Can you just go down? Hardly 29. That's the max that you have. You've taken 50, is it?
No, that will only display that much. You cannot see more than that.
Okay,
That's
fine.
the big problem.
So you see at least even with this 10 values that you see, the most important thing, because the maximum value is at least 10 times this value minimum that you see here. So if you further go down, those further dimensions are not going to add any values, because those eigenvalues will be very, very small compared to the dominant eigenvalue that you have. So what we do in case of SVD or PCA is take the entire information that you have, project it onto a lower dimension, and then try to make sense out of it, or probably try to reconstruct whatever that information that you want using a lower dimension data. Is this clear? So basically, the dominant eigenvalue, the eigendirection corresponding to the dominant eigenvalue, it gives you the direction of maximum correlation. That's all. Okay. So I think we'll stop with this.